So welcome to the afternoon session of the last day. We're very happy to have this project from Caltech. So this talk about mixing type of local Hamiltonians, and this is joint work with Caltech and the network.
Okay, thank you for the introduction. The title of my talk is Mixing Time of Local Hamiltonians, a rapid state preparation via dissipative dynamics. And this is joint work with Jakob Hahn, Hao Li, Zhan Ding, Gan Chan, and Ling Ling. Yeah. Okay, so I will first start with the background, which is the existing results of mixing time and the current mathematical challenges for fluid mixing time. And next, I will talk about our results. And the final part is the outlook. So I think this is the only numerical results in this workshop. And I hope these numerical results can bring more insights. And I think it might be helpful. I think it might be helpful for theoretical analysis of mixing times. Yeah. Okay, so I will start with the background. And the motivation of studying ground states and low temperature gives states are among the most important problems in many body physics and quantum chemistry. So we know that in the community of computational condensed matter physicists and computational chemists, I think most of their times are spent on calculating the ground states or low temperature gives states of many interesting physical models like the transverse field Ising model or Hubbard model, which reflects the physics of physics in materials. And I think a lot of money and resources and time have been put to for classical computation of ground state properties and give state properties. And so yeah, that's why we are focusing on like if it is possible to accelerate this kind of computation using quantum computers. Okay, so if low energy states are very important, then we might ask a question that how does the nature prepare low energy states? We know that for human body, the proteins of human body functions in a thermal bath at temperature T equals approximately 310 K. So the proteins keeps in this temperature by interacting with the human body, which can be considered as a finite temperature thermal bath. And for another example is the high temperature superconducting material. And if you want to cool this kind of material to the superconducting phase, you can simply by putting it into liquid nitrogen, which is the temperature is about 77 K, and you can get you can like lower the time, but you can get it to the superconducting phase by lower the temperature. Yeah, that's by so now we know that nature prepares low energy states just by coupling it with low temperature thermal bath. So recently, a series of quantum algorithms has been proposed to simulate this the dynamics in nature. It simulates the dissipative dynamics in nature to prepare give states or ground states of quantum many-body systems. These linear-Bardian-based algorithms are just like this, as many people have talked about in this workshop. It has a coherent part, and the first part is the coherent part, and the second part is the dissipative part. And this linear-Bardian has nice properties, which firstly they has a ground state or give states as their fixed points, and the second property is that they can be efficiently implemented on a quantum circuit. Yeah. So in this talk, I will mainly focus on the ground state preparation algorithm proposed by Zhan Ding, Anthony Chen, and Ling Ling last year. So the linear-Bardian is like this. And the main idea of this ground state preparation algorithm is a shoveling process. That if you started from, say, a maximally mixed state and you want to prepare a ground state of the system, by running this linear-Bardian, you can shovel all the high energy parts of the state to the low energy states, and finally you can get the state with the lowest energy, which is the ground state. Yeah, so we have three for this simulating nature algorithms. We have we need three requirements. The first is the correctness, which means the ground states or Gibbs states must be the correct fixed point of the algorithm. And second, it must be implementable. That means it can be efficiently implemented on a quantum circuit. And third, it must be efficient. That it means the algorithm needs to converge to the correct fixed point, which is the ground state or fixed or Gibbs states, in polynomial time. For this linear-based methods, the first two properties are easy to satisfy. But the third property is a main open question, which is called the mixing time of invariants. And it is mathematically very challenging to analyze. And this is also the main focus of my talk. Okay, so let's see what's the existing results on mixing time of quantum systems. And previous methods are mainly focused on theoretical analysis of mixing time of quantum systems. The first is that gaps of invariants for preparing Gibbs states imply fast mixing. A more accurate statement is that an inverse polynomial gap of the invariant implies order poly n mixing time, and a constant gap implies order n mixing time. There's another property called rapid mixing, which is faster than this fast mixing property. If you can prove that a invariant has a positive log sublift constant, then this means it can converge to the steady state in order log n mixing time. But the second property is much more difficult to prove than the first one. So let's see what are the existing results on theoretical analysis of mixing time. So I think most of the current results are focusing on Gibbs state preparation for commuting local Hamiltonians. So the first existing result is for 1D commuting local Hamiltonian. I think Fernando Brando and Michael Castellano proved, and Michael Castellano proved that the Gibbs sampler of 1D commuting local Hamiltonian is gapped. So this implies order n mixing time. And I think in 2021 or 2022, I don't remember, a group of mathematicians has improved this mixing time bound from order n to order log n by proving that there exists a lower bound for the log sublift constant. Yeah, and but this 1D commuting local Hamiltonian is well understood, but for the 2D case, it's not that well understood. The only thing we can prove that is the only thing we can prove is for some specific models in 2D, like for example 2D Tori code. I think Aliki proved that the Gibbs sampler of 2D Tori code is gapped, thus it implies order n mixing time. But for so for the commuting local Hamiltonian, we have many existing results. But for the non-commuting case, the only existing result is at high temperature, which I think can be proved earlier this year that the high temperature at the high temperature phase, the CKG linear body of commuting local Hamiltonian is gapped, so it implies an order n mixing time. But for the general case of non-commuting Hamiltonians, it is widely open. And the current stage for ground state preparation linear body is still widely open, both for commuting and non-commuting Hamiltonians. And we don't know how to prove a mixing time for ground state preparation linear bodies. So we are facing serious challenges in theoretical analysis of proving that improving mixing times. The first major challenge is that the invariant of non-commuting Hamiltonians are quasi-local. And if we want to prove the gap of this quasi-local invariance, we need to analyze what is the effect of this exponential decay in tails on the gap of the invariant. And I think, in fact, I have been working on this problem for a long time, and I have discussed with a lot of experts in this area, and our conclusion is that maybe some truths in quantum information theory is missing, and we don't know how to solve this problem, and their mixing times are still widely open. And the second major challenge is that current mathematical tools for proving mixing time do not apply to invariants for ground state preparation. Previous methods on proving gaps or log sublift constant are based on that the steady state is full rank, for example, give state. But if the steady state is ground state, which is not a full rank state, we don't know whether a gap implies fast mixing or log sublift constant implies rapid mixing. Yeah. So for ground state preparation, we don't know what kind of quantity implies fast or rapid mixing. And I have also discussed this problem with many experts in this area, and they said this is a long-standing problem for invariants. So yeah, I think this is also another major challenge. And the third is that it is difficult to improve order poly n mixing time to order log n. If you want to prove rapid mixing of some invariants, it is much more difficult than proving order n mixing time. The example is the 1D commuting local Hamiltonian, that proving the proof of rapid mixing is much more difficult than the proof of fast mixing. We expect the same thing to happen for all the other cases.
The second point.
Yeah.
Sorry? What's the conjecture?
Conjecture of what kind of quantity implies fast mixing of ground state.
No, the second point, the ground state. So I conjecturing that like 1D commuting local Hamiltonian can be prepared efficiently using this annealing type of invariant.
The conjecture is based on our numerical method, our numerical results. So I will talk about our numerical results first.
Yeah, sure. But could you summarize the conjecture?
The conjecture is that we have rapid mixing for 1D local Hamiltonian, for gapped 1D local Hamiltonian.
So for gapped 1D local Hamiltonian, you have polygon mixing.
We have log n mixing.
Log n mixing. Okay.
Yeah, that's our conjecture.
Okay.
So these are the major challenges in proving in theoretical analysis of mixing time. So next, I will talk about our results, and our results are mostly numerical, and I think we can provide insights and maybe can help theorists to show to theoretical proofs of mixing time. So we will start with the simplest example, which is quasi-free systems. We consider a quadratic fermionic Hamiltonian, which describes the single fermion hopping between different orbitals of Hamiltonian. So this CI-CJ dagger is just a hopping operator between of electrons between different orbitals. And the jumper operators are annihilation and creation fermionic operators. So for this simplest case, we show that the invariant preparation, the ground state preparation invariant have a closed form of the one-body density matrix. The one-body density matrix, we show that the one-body density matrix is exponentially converging to the ground state distribution PF. Yeah. In fact, this ground state preparation invariant can be simplified to this case, which is dp dt equals minus p minus pf. So this means the one-body density matrix P is exponentially converging to PF, and the converging rate is independent of system size. Sorry. Oh, sorry. K is the Yeah, this K is some Fourier transform based on the coupling operator K, A, yeah. Sorry. Okay, so we know that one-body density matrices are exponentially converging to the ground state distribution. And using Wick's theorem, all the K-body density matrices can be derived from the one-body density matrix. So all local density matrices are exponentially converging to the ground state at a constant rate, independent of the system size. Okay, so this is a result for fermionic systems, and we find that some local Hamiltonians with poly jump operators can be converted to these quasi-free systems. The first example is the transverse field Ising model with coupling operators on the boundary, which is x1 and y1 are the coupling operators on the first qubit, and xn, yn are the coupling operators on the last qubit. So, so this is the Hamiltonian of transverse field Ising model, and we choose the choice of this f omega is the strength of the jumps, which means that this for omega less than 0, which means it jumps from high energy to low energy, the jumping strength is always 1. And for jumps which jumps from low energy to high energy, the jumping strength is 0. So this ensures that this linear always shuffles the high energy parts of the state and transits it to the low energy parts. And so in this simplest setting, that which is the boundary dissipated transverse field Ising model, using Jordan-Wegener transformation, we can convert the linear to a quasi-Fourier form, and we can also obtain a closed form of one-body density matrix. And so we can directly simulate the dynamics of this linear for very, very large system size. Okay, so this is our numerical results. These are two matrices. The first is matrix element of poly operator x1 in the computational basis. This is simply the two diagonal matrices on the off-diagonal block. And the second matrix is the matrix element of poly operator in the energy basis. This means that this x1 poly operator allows jumps between different eigenstates, allowing energy transitions. Yeah. So this is our numerical results of the dynamics of boundary dissipated transverse field Ising model. The first plot is the energy decay of the linear dynamics, and the second, and in this quasi-free setting, we evaluate the mixing time using the energy decay rate. We can see from the first plot that we start from a maximally mixed initial state and run the linear dynamics. We can show that we can see that the energy, in fact, the energy is exponentially decaying in time. It means that the energy is exponentially converging to the ground state energy. We did the simulation for equals 10, 20, 30, and 40. And we can see that from this log-log plot of mixing time scaling, we can see that the mixing time scales polynomially with system size. And the scaling is approximately T mix equals 1 order n cube. Yeah, and we are trying to proving this results using perturbation theory, and yeah.
The theorem you mentioned, like explanation.
No, this is because that for this, you know, these are two different settings. The first setting is that this jumper, we have many jump operators here. The CK, C dagger are all the jumper operators on all the orbitals. But here, for transverse field Ising model, only the first and the second, only the first and the last qubit jump operators can be converted to like fermionic operators. Yeah. So local fermionic operators. So we use only the boundary dissipated jump operators. Yeah.
There's another solution. After convert that to the Mariana operator, you could, in principle, apply the all the local Marianas, and then the previous theorem will apply. But that's not the physical setting. The physical setting is to apply all the spin operators, the coupling operator, and that one we don't have to because it's not good.
Okay. Thanks for the question.
So here you're saying you're only adding thermostat on the boundary. So what happens if you put in everything, like on every mode?
If I put the jump operators, this fermionic jump operators on every mode, so the energy, for example, the energy is just a two-body operator. So the energy would converge to the ground state energy exponentially fast, and the convergence rate would be independent of the system size. But if I put the jump operators only on the boundary, I will get a mixing time which will scale like n cube.
So the n cube is really about this only thermal lines at the boundary.
Yes, right.
And also, his question is about what if you put like all the spin operators.
Oh, that's the next slide. Yeah. Okay. So another quasi-free example is the cluster Hamiltonian. We call this cluster Hamiltonian because each local term is x dx, and they are commuting and frustration free and local. People use this Hamiltonian to prepare cluster states, and that's why we call it cluster Hamiltonian. And we add additional magnetic field. So in this case, we also choose the coupling operators to be on the boundary, and the parameters are chosen to be h1 over j equals 0.1, which makes the Hamiltonian in the SPD phase, and the Hamiltonian in this phase has a four-fold degenerate ground states. And this open system can also be converted to a quasi-free form, and we can also simulate the dynamics of very large system size. And the left panel is the energy decay of Lindbardian dynamics for different system size. We can show that the energy is exponentially converging to the ground state energy. And the left panel is the mixing time of the open system. It's a log part of the mixing time. And we find that for different h over j values, it always shows that T mix is about order n cube. So yes, I think we are working on the theoretical explanation of this n cube scaling of mixing time. Yeah, I think there should be an explanation. Yeah. I asked some people before. I asked Michael Castellano before about this. He said that there are two kinds of systems. One of them is diffusive, and the other kind of is. Yeah, I think it depends on the property of the Hamiltonian, whether it's diffusive or some. Yeah, he told me that the mixing time of boundary dissipation should be between order n square and order n cube, but we don't know whether this is correct.
Because this is like KFI without this order, and therefore after we turn that into the quadratic Marianas, that's it, and then the slowest mode. There's this energy transition. The slowest mode is like a sine. And that one, the square, the magnitude is like 1 over n squared, which means that you just go through this once, probably just increase like 1 over n squared. The chain is a blank. But this is not proof.
Yeah. Okay. Thank you for the question. The previous two examples, these two examples are about quasi-free systems. But we know that for most of Hamiltonians and most kind of jump operators, they are not quasi-free, and there is no closed form of the one-body density matrix. So for simulating this Lindbardian dynamics, we are using another kind of method, which is the tensor network method. We represent all the operators as matrix product operators. That means we represent this quantum state rho and the Hamiltonian H and the jump operator K as matrix product operators, and evaluate the mixing time by directly propagate the Lindbardian dynamics. And the mixing time is defined like this. So we start from the maximally mixed initial state, and we define the mixing time as the minimum time we need to reach 0.5 fidelity with the ground state. Yeah, I think this is a reasonable definition. And the effective of these tensor network methods are based on assumption that because we are representing all the operators as a matrix product operator, we need the assumption that all the jump operators and the states during time evolution has low bound dimension structure. If we are propagating this Lindbardian dynamics, we need to multiply these operators together and multiply this matrix product operator together. So it will say the bond dimension of rho is D, then the bond dimension of K rho K dagger should be D cube. So after each time step, we need to compress the bond dimension of rho. So the main difficulty here is that we need a faster compression method. Because the direct tensor network compression is very, very slow. Based on SVD, it's very slow. So we use approximate fitting methods and run it on GPU, and it's 100 times faster than the direct compression method. Sorry? Okay, you just use, you don't compress the bond. So if you want to multiply 3 matrix product operators, you don't calculate the you don't apply SVD. Instead, you are using a new MPO to approximate this K rho K dagger. No, I think it's just it doesn't have a name. It's just approximate fitting. Yeah.
So why people don't use it earlier?
Oh, because
people earlier.
oh, because
people use SVD all the time.
Yeah. Because because this kind of Lindbardian dynamics requires very, very large amount bond dimension compression. So that's the main cost of this simulation. So I think previously people there's not too much need for this. Yeah, there's no computation task that needs so many times of compression. What's TCI?
Sorry, carry on.
Okay. So and next we will show that our assumption is true. I will verify the low bond dimension assumption by showing that the tensor network result. Sorry.
It seems like also a little bit surprising to me that this type of propagation has indeed not been studied a lot in the literature. The reason is that, for example, you propagate this from, let's say, RK4, right?
Yeah. So
each step you have also compression indeed to jump operators and also RK4 itself and the concept. And each of the case that's really an MPO. I mean, this is considered to be too expensive for most other studies. Previously, the jump operators are always much more local. So it's just, yeah, I mean, it's not an energy optimization problem either. It's not like BMRG and optimize one side, move to the other side. It's just a very few people have worked on
Oh, because the jump operator is already very extended because it's
Yeah, the
linked
jump,
to
yeah, exactly. Yeah, so every time you're literally sandwiching, there's a cone like MPO, 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 boom. Do this again and again and again. So it's not very difficult setup. But maybe, I mean, which also indicates that there's probably a huge room for optimization.
But the thing is because you want converge against state. If you have an arbitrary body with very local jumps, then the simulation will be much faster. You probably can
With the
use
very local ones, there are different techniques to avoid this.
Okay. So I have told that we need the assumption that all the jump operators and the states during time evolution must have a low bound dimension structure. So we verify this assumption by showing that the tensor network results with different bound dimension matches each other very well. So this is the simulation of n equals 20 transverse, the bulk dissipation of n equals 20 transverse field IC model. The bulk dissipation means that we have jump operators on each side of the local Hamiltonian. And we use like different bound dimension to do the computation. And we find that they match each other very well. They're almost the same. And the relative error of these two results are less than 0.1%. So this shows that the results of tensor network methods are reliable. Okay, so now let's start using our new tensor network results to analyze the mixing time of non-commuting Hamiltonians. The first example is a Heisenberg model in a magnetic field with also boundary dissipation. These jump operators are x, y, z on the first qubit and last qubit. And this is a log-log plot of the mixing time with respect to system size. And this numerical result shows that the T mix is approximately order n to 2.5.
I guess the reason why you're only using a small field jumper A is because that also makes your simulation faster. That like everywhere, then the simulation also will be rotated, correct?
No, because we are discussing boundary dissipation here. So I will discuss about later. Yeah. Okay, so now we can arrive at a conclusion that for the cases we have evaluated, boundary dissipation of 1D chain always lead to Pauli mixing time. Yes, without disorder. Yeah, I should be more rigorous. Boundary dissipation of 1D translational invariant chain will lead to Pauli mixing time. Yeah. Sorry?
Didn't you only use X before for the dissipation? Why do you need all the polys?
We also try like a single poly, and I think it works. But
Wait, there's a current.
Yeah, at least for transverse field IC model, only a single jump operator will work. Yeah. Okay. Yeah. For this model, I think we need we need at least 2 jump operators. But I choose 3 because this would make the simulation faster. Yeah. But the results of the scaling of the mixing time will be the same. Yeah. So
Try also these things for final temperature state.
Final temperature is the next step.
Oh, okay. Yeah. So you also have precise later.
So yeah, previous examples are boundary dissipation, which we only have jump operators on the boundary. So now we try
In the future.
for transverse field IC model Hamiltonian. In this case, we use all the 3 and Pauli operators. That means x, y, z on all the sides as coupling operators. And we plot here the mixing time versus log n. And we simulate the dynamics from n equals 6 to 30. These data points are 6, 10, 15, 20, 25, 30. And this result shows that the mixing time is order log n. And we also try another example, which is the Heisenberg model in a magnetic field. We plot this mixing time versus log n, and we do the simulation from n equals 6 to n equals 30. And our numerical results also shows that the T mix is proportional to log n. Okay, so we go back to this. These are the main results of my talk. So now we have seen that many people are trying to analyze the mixing time theoretically, and they are facing like serious challenges. The first is non-commuting, a second is ground state preparation, and the third is rapid mixing. They have many serious difficulties. However, our numerical method doesn't have all these difficulties, and we can directly show strong evidence of rapid mixing in non-commuting Hamiltonians for ground state preparation. And so it doesn't have any of these three difficulties. And now we can go back to the chart of existing results. So for ground state preparation, we now know that from our empirical results, we know that for 1D gapped local Hamiltonians, if you use boundary dissipation, then we would get all the poly mixing time. If you use bulk dissipation, we will get all the log mixing time, which is rapid mixing. Okay, so for non-commuting Hamiltonian, for the gibbs state preparation of non-commuting Hamiltonians, I think our tensor network method would still work, but that will be the next step of our work. Yeah, I think that's the almost all the results for this talk. But I will finalize. I will talk another interesting observation that empirically we find the mixing time of the Lindh body can often be characterized by the non-Hermitian path. So this k rho k dagger term is the term that we added for ensuring the CPTP of this Lindh body. But we find that by removing this transition part, we can also characterize the mixing time for Lindh body by analyzing the term h plus I k dagger k. So these are two examples that for boundary dissipated TFIM, the non-Hermitian part also has order 1 over n cube gap, which means the mixing time is n cube. And for bulk dissipation, bulk dissipative TFIM, we directly propagate this Lindh body and normalize the density matrix after each step, and we find the direct propagation of Lindh body also shows all the log n mixing time. Yeah.
So here you mean that you removed the dissipation?
We remove this red cross part, which is the transition part.
So so it's not trace preserving, right?
Yes, it's not trace preserving. So we need to normalize the density matrix after each step.
Does it go to ground state?
Yes, it goes to ground state.
Why does it go to ground state?
This
is I think this k dagger k is enough to shoveling all the high energy states to the low energy ones. We add this k rho k dagger simply only for the CPTP for ensuring CPTP of the Lindh body.
the ground state is a fixed point. Whether this dynamics is good, it's certainly not CPTP. So because this ground state is a fixed point of each k, and therefore you remove the transition parts, ground state is still a fixed point. Whether it's orthogonal, we don't know. But the idea is that you were in the thermal case, we have been trying to find this parent Hamiltonian, as we heard this morning. For the ground state one, we don't have such a thing because sigma is singular. So let's say we just remove that transition part. We immediately have a Hamiltonian like object. And we ask, what is the gap of this thing? It turns out there's not always. There are some cases you can prove, but most cases, I mean, they're different, but it seems like they're not too far away from each other. But physically, what it's like is you can think this interlocking does is it does like a you have this Poisson process, it decays and then jump back. Poisson decays, jump back, and it seems like the gap is mainly characterized by decay.
So in particular, the energy is not descending for this process
Energy is not
Energy is descending.
because you're saying that jump back, right? So energy is descending.
Yes, energy is descending.
So but if you just knock off the third term, it's the second term. And also the normalization of the trace series.
Block out the second term, the H row.
It would be similar to
okay. Yeah, but the thing is, the second one is a growth, right? So the thing you're trying to avoid is the vectorization process, right? The K dagger on the right is really the one that kills you. So all of this kind of synchronization is to avoid that issue. Let's say we just kill it.
no, but this is not a Hamiltonian, right? So H plus I times K dagger
I
K.
mean, so
It's a complex.
it's not permission. Yeah, I mean, there's a large field really studying these things.
So you can think of it in dynamical terms doing post-selection. So every time something does a jump, it's thrown away and you start again. And if you did a Monte Carlo wave function propagation, this would be the part where you add the non-Hermitian term to allow for the fact that on average, you'll have decay because of the jumps, but you throw away individual jumps. There is actually a Monte Carlo, you might find that useful. There is a Monte Carlo, a classical Monte Carlo procedure to simulate things, quantum systems with jumps.
You'll have used that.
Yeah. So this is then just the non-Hermitian
Yeah,
term.
so he presented the MPO version. There's also MPS version, which is exactly
Right.
Yes.
What's the question?
So I also think that this is a little weird because if you remove the second part, essentially you don't have a way to push your high energy state to the low energy state. For example, if you look at KK, what KK do is it will push some high energy egg vector to some low energy egg vector, but after you apply KK dagger, it will go back.
Yeah, the only thing, this is surprising. Yeah, having some relation, with the gap. I mean, that one I can see. But the ground state is indeed a fixed point. I can see.
Yeah.
But other than that, indeed, we shouldn't expect it to mix or something. This is just a way to compute some related stuff.
Okay, so this is thanks for the question, and this is I think there will be no theoretical. There may be no theoretical explanation to this phenomenon, but this is an interesting observation that I want to mention. Okay, so last part I will talk about the outlook. The first thing we want to know is that whether it's possible to prove the mixing time of non-commuting Hamiltonians by generalizing the previous proof of commuting Hamiltonians. As I said, that we are facing like serious difficulty, and we still want to know how to overcome these difficulties. And second is, maybe you can try numerical simulation of linear dynamics of 2D local Hamiltonians. The reason that 2D local Hamiltonians are important because I believe we can achieve quantum advantage in 2D local Hamiltonians. Yeah, so we need to use a 2D tensor network to do the simulation. We know that we believe that there must be quantum advantage in 2D local Hamiltonians, but maybe there might be quantum advantage in even 1D local Hamiltonians because, as I have showed, for bulk dissipation, the mixing time of ground state preparation is order log, and this is super fast. And there might be a possibility that this quantum algorithm can be faster than some of the most popular classical algorithms, and this can be evaluated as quantum advantage in 1D. Yeah, I think this basically is all of my talk.
For two short questions.
Yeah. So I think this is also related with what Zhan said, the open question, right? So you're saying that for the ground state preparation, we cannot use finite temperature like proofs.
Yeah.
This is, if you think about this statement classically, this is completely ridiculous because the ground state in classically is optimization. That's much easier than understand sampling. So why don't we, for example, I mean, you have been working on a proof, right? You probably have already looked at these things, but the standard proof for optimization is that you look at some Lyapunov function, for example, in this case, in energy, and see how energy decays, right?
Yes, yes.
So you probably have done that calculation already, but we shouldn't use the finite temperature ideas to prove the zero temperature dynamics. That's what I'm saying.
Okay, I think Zhan and me also discussed like how to use energy decay rate to prove missing time of this ground state preparation invariant. Yeah, but we don't have much progress yet.
Yeah. So the issue is if you look at the cluster, like the entropy production, right? Where here is like.
No, but this is still finite temperature, right?
Yeah.
For optimization, it's much easier. I mean, we don't need these kind of concepts.
Yeah, unfortunately, once you have this matrix case, at least to the extent of our current knowledge, you just write down that energy decay. That's very the right hand side. First step is very easy. You don't know what to do next. You need to convert that into something that's fancy. That's the main bit.
Yeah.
In some scenarios.
Yeah, I think about this point. I thought I can also try to add one comment. So I do think previously we try to show the energy decay and the wave files. Maybe the reason is we don't have a good Lyapunov function. So maybe we try to add something to the energy and we can get a better Lyapunov.
Yeah, because that could be. But if you really look at Robert's talk, I mean, that's an energy decay argument, and that's, I mean, use the energy decay part is done like a really follow a really simple procedure, and it's hard to generalize.
Yeah, but I mean, there are other Lyapunov functions that we can use that is not energy, like gradient square, for example. Right? That's also very typically used in optimization. I mean, so we should try these things instead of looking at high temperature proofs and try to adapt them to zero temperature.
That would be fantastic. I think that would be fantastic.
Okay. Certainly, I will try those ways to prove missing time for this ground state preparation invariant. Yeah.
Any other questions? All right, no more. Let's thank Yongtao again. At 2:30. Okay, for the last one.